Alright, let's take a look at this circuit here. We have a couple resistors, an inductor, and a current source here with a switch that will open at time equals 0. We want to determine the current going through this inductor, where the switch has been closed for a long time, and it's going to open at t equals 0. So we want to figure out the current IT for t greater than 0 across this inductor. And also, if we have time, let's see if we can figure out, let's also determine the voltage across this inductor for t greater than 0. Okay, we'll keep that at the back of our mind there to solve. Okay, so a couple things here. We're going to have, we're going to treat this as a step response to an RL circuit, and so because of doing that, we can use this following equation. So the first thing we want to do is write down the equations known in order to help you simplify this problem. The equation here is going to be I of t, and you could also call this I L of t, and so I'm going to try to use, I'll probably use them interchangeably, but I at time infinity plus initial condition current plus I at infinity, all that times an exponential function to the minus t over tau. Okay, so this is the equation we want to solve for to answer this question. And a couple things here, what we need to figure out to solve for this problem is we want to figure out, let me go ahead and click on this here. We want to figure out time infinity, the current here, the initial current, and we want to figure out our time constant. Okay, we can figure those out, then we can just plug those in there and we figure out the current as a function of time for t greater than 0. So a couple things. Another thing we want to add here is we want to add the equation for the time constant. So the tau is going to be L over R. So keep that in mind as we're solving for this problem. So as we did for a previous problem using the RC circuit, we can break this up into different time components. So the first thing we want to do is we want to say, well, when time is less than 0, okay, that means the switch has been closed for a long time. So here, switch is closed. Okay, and in this case, I want to show you two methods. So I'm going to say method 1. Okay. So method 1, I want to show you two ways of doing this. Of course, there are more than these methods, but just to give you an idea. So when the switch is closed, we know that the inductor is going to be behaving like a short circuit. Okay, so we have a short circuit. Okay, so we can redraw this circuit here. So let's redraw it. And what happens is we're going to have our resistor, and here's our switch, here's our inductor, here's our resistor, and I'll complete the circuit in a second, and then we have our current source. Okay, 6 amps. This is going to be 10 ohms. This is going to be 5 ohms. So our switch is closed and our inductor is closed. Okay, and our current is going to be flowing this way. So our I sub L, or our I, is going this way. Now a couple things we know, because we have two short circuits there, our current's gonna is going to follow the path of least resistance. So pretty much our circuit's gonna be this guy. So you're gonna skip the resistor. So essentially our circuit is just the 6 ohms. Excuse me, the 6 amps. So essentially this is what our circuit looks like. Okay, 6 amps here. And why is this important? Because this is going to be our I. Let me go and switch here. This is going to be our I of 0. Is going to be essentially our I, which is 6 amps, and we could also call this I sub L of 0, or in another notation you'll see I of 0 to the negative. So all that is the same, so essentially our initial current is 6 amps. So we solved for I of 0 in the above equation. Okay, so that's one method. Another method, probably not as popular, but we can actually use a source transformation. So we can say, well, let's try method 2 here. And this is method 2 just for t less than 0. Okay, for t less than 0, the same conditions. And in this case, I want to use a source transformation from previous chapters. Okay, so if we do that, what we're going to come up with is, so what are we going to do? What are we going to transform? We're going to take this current source with this 10 ohm resistor, and we're going to transform it into a voltage source with that 10 ohms in series. So now you got the 6 amps with a 10 ohm in parallel. We're going to switch that to a voltage source in series with a 10 ohm. That's essentially what we're going to do. And what we come up with is, again, I'm going to redraw the circuit like this. We've got our switch here, and this is going to be like this. We're going to open it at t equals 0. We have our inductor, we have our resistor here. Oops, actually the resistor, we just did a source transformation, so that resistor is going to be now in series with the inductor, and instead of a current source we're going to have a voltage source. Okay. Alright, I'm going to go ahead and write this. We still have the current going this way, I. We have our inductor 1.5 henries here, and we got 10 ohms here, the 5 ohms there. Remember, in this case, before I get into the final circuit, to get this value here, the way we get this value is by using the source transformation equation. So to get the voltage source, it's just the current source times the resistor that we're dealing with. In this case, our current source was 6 amps. The resistor we're dealing with was 10 ohms. Okay, so that gives us 60 volts for our voltage source, and that's going to be this guy here. Okay, but let's go ahead and simplify this again, because again this is going to be shorted. This guy is going to be shorted there. We're going to be short, so we can rewrite the circuit in terms of the source transformation as this guy, and then we got a voltage source here. Okay, this is 10 ohms, this is 60 volts, the current's still flowing this way, our I. So the point of this whole thing is we want to figure out what I is, so we can pretty much just use Ohm's law here. So we know I equals V over R. This I again is going to be initial I, or I at 0 to the minus there. So it's just going to be 60 volts over our 10 ohms, which gives us 6 amps again. Same as we had before, it's just a different way of going about solving for the same thing. Okay. So it's a different way of solving for the same problem. So two different methods. Again, we're not limited to these methods, but I just wanted to share that to you. So we figured out our initial current. Let's look at the time when we're at infinity next. So I'm going to scroll up. Okay. So when we have time equals infinity, that means the switch is open in this case. Okay, and in this one I want to show you two methods as well. So I'm going to do method 1. Okay, and I'm just going to do a current divider. Okay, for method 1. Alright, so for this, because the switch is open, I'm going to go ahead and draw the circuit here. We got our 5 ohms, circuit's open, the switch is open, excuse me, and because it's been a long time, the inductor is pretty much going to behave like a short circuit. We have our resistor here, and we have our current source here. It's 6 amps, this was 10 ohms, this was 5 ohms, and then our current is still going through here. Alright, so our circuit in this case, we have a 6 amp with a 10 ohm and a 5 ohm resistor set up in this fashion. So what we can do is use a current divider to figure out our I in this case. So our I in this case is going to be our I at time infinity. It's going to equal to, we're using current divider, it's going to equal to 10 over 10 plus 5 ohms times the 6 amps. Okay, and we solve for that, we get 4 amps. So we just solve for at time infinity. So we're done there, but I just want to show you another method of doing the same exact thing. Okay, so let's do method 2, and in this case let's just use KCL or nodal analysis. Okay, I'm going to redraw the circuit. It's going to be the same thing. Come down here. Here's our circuit. Our 6 amps here. In this case, what we're going to do, again, our current is going this way, our I. In this case, I'm going to call this node V. I'm going to ground my circuit there. And then, of course, the 5 ohms is there, 10 ohms is there. Okay, so I'm going to do KCL at V, and pretty much says the current going in is equal to the current going out. If I solve for this, so I got 6 amps is equal to, okay, let me back up a little bit. I'm assuming, of course, we got this current going in here, and I'm assuming current coming down here, and then current coming down there. Okay, so one current going in, two currents going out. So 6 amps is equal to V over 10 plus V over 5. Alright, and if we simplify this, essentially what we get is, we rearrange this, we get V equals 20 volts. Okay, and then using Ohm's law, I equals V over R. Our V in this case is going to be 20 volts. We just solved for. The R we're dealing with here is going to be the 5 ohms, and that's going to give us 4 amps. So another quick way of coming up with the same solution using a different method. And of course, what I didn't mention is this I is I at infinity. Okay, so we have solved for we solved for I infinity, I 0, I infinity. Now we need to figure out our tau. So our tau, let's back up here and let's solve for tau, and we can plug this in. So tau is for t greater than or equal to 0. We can redraw the circuit and we get a resistor, our inductor, our other resistors here, and then our current source is here, 6 amps, 10, this is 1.5 henries, and this was 5. Okay, the current is still over here, and we know our tau is going to be L over R. In this case, we need to figure out our R equivalent. Okay, so a couple of things we can do. We can do an equivalent circuit where, in this case, we can turn off the current source here, so we can have an open circuit. Okay, and that would leave us with the two resistors in series. So we got R equivalent is equal to 5 plus 10, which is going to give us 15. Alright, we don't care about the current, but if you did want to solve for the current, we'd go back to again the source transformations and solve for the current. In this case, we don't need it, so we just need the R equivalent to plug into this equation up here, and we already know our L, which is 1.5 henries, so we got 1.5 over 15, and that's going to give us 0.1 second. So that's the final part of our puzzle, which is our tau. Okay, now we can go back to the original equation, and the original equation was this guy here. So this was our original equation. So now we just plug those numbers in. I'm going to come down here and plug those in. So we got I of t, we can call I sub L of t, the current going through the inductor, is equal to 4 plus 6 minus 4 e to the minus t over 0.1. We simplify that, or further plug that in, get 4 plus 2 e to the minus 10 t amps, and this is going to be our I sub L of t, and then this is the solution to this problem. Alright, let's go ahead and take it one step further, and let's just say what is V of t, VL of t. Okay, let's look at that. So VL of t is essentially L di over dt. Alright, so that's going to equal to 1.5 henries. Okay, di, which is that function we just came up with, 4 plus 2 e to the minus 10t over dt. Alright, so we simplify this equation, or solve for this equation. We get 1.5 times minus 20 e to the minus 10t, and then further simplify this and we get minus 30 e to the minus 10t volts, and this is going to be VL of t. Okay, so that's how you solve for both the current and the voltage across this inductor, using this methodology and using this equation there. Alright, so that's the practice problem 712, step response of an RL circuit, and final solution is here. you could always plug in a time value here if the problem asks for that, and solve for that value accordingly.